Consider a situation where the system is saturated and there is a sand layer on top of a clay layer on top of a sand layer. And then we apply a very extensive load on the surface so that the area and the dimensions of the load in X and in Y are much, much greater than the thicknesses of the layers that we are talking about. So we truly have a one-dimensional system. Now, before we apply the load, because of the hydrostatic conditions, the pore fluid pressure increases linearly with depth. This is the pore pressure initial. Once we apply the load, and we're going to play a little bit a game of times here, we're going to apply the load very fast with respect to the clay, but not fast enough with respect to the sand. Therefore, the sand will drain all the excess pressure, but the clay will not. Therefore, if we apply a load Q here, and if the water cannot drain, the water is going to take all the load. And we're going to see a jump in the fluid pressure here, which is going to be equal to Q. This is an excess pressure. And if we wait long enough, this pressure will disappear and it will go back to the hydrostatic condition. Probably will drain first from the edges, and then as time passes by, it will continue squeezing water out until all the excess pressure will eventually vanish. This process of the excess pore pressure escaping is what in the geotechnical field we call consolidation. Please be careful, because the word consolidation in other fields, like petroleum geomechanics, means that it is a cemented soil. Here we use the word consolidation to refer to the process of the excess pressure dissipating. In order to understand this a little bit more carefully, let's consider an element at some elevation in the middle of this clay profile. So we are actually looking at this element at a certain depth Z, and we realize that the water, let's draw the center line here, the element at the bottom is squeezing, and the excess water, or the water that is escaping, is moving through the upper element, but the other upper element is also squeezing, and so there is more water coming out of this element than the water that came in. So this is the flow that came in, and this is the one that came out, in such a way that Q out is equal to Q in cubic meters per second, plus the change in the volume of the element in a given period of time, so the rate of change in the volume. Now, at any point, if you plot the Q in versus Q out as a curve, so then we can say that Q out is a Q in plus a gradient times delta Z. Therefore, let's replace here, and Q out is equal to Q in plus dQ dZ times dZ. This is, we are adding this quantity. dQ dZ is the slope times dZ. We're adding that quantity over Q in times Q in. And now, because we're working with differentials, we're going to convert this one also into a differential. And so this is the change in the total volume. But really, the total volume, when it is changing, what is actually changing is the volume of voids. So from the volume total, we are going to refer to the volume of voids. And so now we can replace these quantities by the volume of voids with respect to time. Now the Q in and the Q out cancel out, and we remember that Q is equal to KIA from Darcy, where I is the change in total head with respect to Z, that is the direction of the gradient, times area, which is dx dy. So let's keep it as an area. And when we bring it here, now we have the d with respect to Z of K may be varying, so we're going to keep it inside K. The gradient is dH total with respect to Z. Now the area, the cross-sectional area, horizontal, will remain constant, so area times dz becomes here, but we can send it to the other side, so it's going to be area times dz here. Now the volume of voids is related to the volume of solids by the void ratio. So volume of voids is going to be equal, remember, volume of voids over volume of solids is equal to the void ratio, so it's the void ratio times the volume of solids. Once again, the volume of solids, we are going to assume that it's not changing, so we can take it out, and this becomes the volume of solids times dE dt. But the reason why the void ratio is changing in time is because the effective stretch is changing in time. So now we can say that dE dt is equal to dE d sigma effective times d sigma effective dt. Furthermore, sigma effective is sigma minus u. So this becomes dE d sigma effective times d sigma total dt minus du dt. Now we can replace here, but I would like to make one more substitution. Notice that AdZ is the total volume, so this quantity here is the volume of solids over AdZ is equal volume of solids over volume total, and which is equal volume of solids over volume of voids plus volume of solids. Therefore, if we divide numerator and denominator by the volume of solids, we get 1 plus E plus 1, so 1 plus E, just to keep it nice. And now we can do all these replacements. The dz of K dH total with respect to dz is equal to 1 over 1 plus E times dE d sigma prime times d sigma total with respect to time minus du with respect to time. The only additional substitution that we can do at this point is to replace H total is equal to H elevation plus H pressure, which is equal to H elevation plus fluid pressure over gamma water. And so this can come here, but the derivative of that with respect to Z, the change in elevation with respect to Z is 1. So if we replace it here, this will become 1 plus du with respect to gamma water, but we can keep it in that for now because I'm going to make few additional substitutions. So let's write it down just for completeness. dz is K, and d with respect to dz of H total, which is equal to H elevation plus U over gamma water, is equal to 1 over 1 plus E dE over d sigma prime d sigma total with respect to time minus change in pore pressure with respect to time. This is a very general form of the one-dimensional equation, and it's really worth observing before we go any further. This is really highlighting the fact that the rate of change in the total energy will be related by the volumetric changes that are taking place in the material, and to some extent, and then to a large extent, the rate at which the pore fluid pressure can escape, which is controlled by the permeability. Now we're going to make a couple of assumptions. The first one is we're going to assume that K is constant. So if K is constant, then it can come out of the equation, and I can put it in the denominator here. And if that is the case, now I'm going to have the second derivative of this, and the second derivative of the elevation with respect to z goes to 0. The first derivative is 1, the second derivative goes to 0. So what I get here now is the second derivative of u with respect to z twice, and I have sent to the other side k that goes into the denominator, and gamma water here was in the denominator goes to the numerator, 1 over 1 plus E. And we can make one more assumption, so this is dE, this sigma effective. Let's assume that this sigma, that the load that I have applied does not change with time. So if in addition I make this assumption that the externally applied total load is constant, then this term cancels out, and I get minus du dt. But this negative sign, let me add it here. Why? Because the void ratio decreases as the stress increases, so this has negative slope. So right now, all this is a positive quantity. So with those two assumptions, and if I call all this a new constant, which you may wonder whether it is a constant, but now I flip this one to the other side, and I'm going to call that the second of u with respect to z twice, and here is the constant Cv is equal to the time rate of change of the pore pressure with respect to time. Several important observations here. Number one, this equation is exactly a diffusion equation for chemical components, for thermal diffusion, chemical diffusion. In chemical, this would be the concentration C and the concentration C, and this would be the chemical diffusion coefficient, typically letter D. In thermal, this would be temperature. U would be temperature, but this is a typical diffusion equation. So we can call consolidation a typical diffusion problem where the variable that is diffusing is the pore fluid pressure. This is really quite an interesting way of looking at it, because it puts us in a mathematical framework as well as in a physical framework. Consolidation is pressure diffusion. What I am always concerned is about all the assumptions that we make. And so let's review these assumptions together, and let's begin identifying some of them. Here we are saying that all that goes out is equal to what goes in plus the change in volume in the element. So number one, here we have mass conservation expressed in the form of volume, which is always tricky, but it is really what we are assuming. So this is one assumption. The other one that we are assuming, that all the fluid that goes in was not used to saturate this element. This element was already totally saturated. And so we are not changing the saturation, so the saturation, the degree of saturation is 100%. Number 3, when we are saying that the change in the total volume is only due to the change in volume of voids, we are assuming that the volume of solids is constant. In other words, that the bulk stiffness of the mineral is infinite. Then we replace Q for Darcy. We are assuming that that linear law applies. And as we move further, notice that here to make the final derivation, we assume that permeability is constant. Now permeability may be changing with depth, but also permeability is going to evolve during the process, because as the soil gets squeezed in, this sponge squeezes, the pores get smaller, the pore throats get smaller, and the permeability will decrease. So this is not totally true. For most general cases, it's not. And we are assuming that the load was instantaneously applied and that it remained constant thereafter. And that may not be the case for your problem. For example, you build a dam gradually, or you make a building foundation and then we gradually build the different floors and apply the load. And that time scale of loading may interact with the time scale of the diffusion process, and you cannot separate them in taking this extreme. You will have to keep it into the picture. There are a large number of assumptions that we are making all the way through, and if for some reason some of them do not apply, you cannot go automatically to the last equation. You have to come closer to the surface. In particular, we assume that this quantity here is a constant. But notice that the void ratio is changing because the effective stress is changing as the excess pore pressure escapes. So the void ratio is not constant, and so this compressibility with respect to 1 plus E is going to be changing, and the permeability is going to change as well. So this parameter is not really constant unless you are in a narrow regime where this is taking place. In a broad range for large significant changes in effective stress, this will not be true. But derivation is correct. By the way, we also assume that this was a one-dimensional case. If your load is not infinitely extensive in X and Y, then you're going to have drainage also in X and Y, not only in Z. So you have to make the analysis more complex by taking the three-dimensional axis or the axisymmetric conditions in a well, for example. But this is really such an elegant derivation. Before we go to the next step, let's complete here by making a couple of additional comments. One is that if you look at the units of CV, and you can look at it coming from permeability and the effective stress and the unit weight or here, the units of pore pressure will cancel out kPa, but the units of CV have to be the inverse of the units of time with respect to distance square. So the units of CV are in meter square per second or meter square per unit of time, per day, per year. Number one. Number two, if we go back to the interpretation of what this CV, coefficient of consolidation, or the pressure diffusion coefficient, what it actually means, please look at this constant that we have encircled here. The change in void ratio with respect to 1 plus E, so change in void ratio with respect to 1 plus E, if you analyze it carefully, this is volumetric strain. So this is volumetric strain with respect to, in one-dimensional cases, the one-dimensional contraction, a vertical strain. With respect to sigma prime, this is the constraint modulus. In other words, the inverse of the constraint modulus. So this quantity here is a stiffness, and this is permeability. Therefore, the coefficient of consolidation combines transmissivity component, which is the permeability or the hydraulic conductivity in this case, and a parameter that relates to the ability to store water in the system. So this is a storativity. And This is always the case for diffusion systems: electrical, chemical, thermal, mechanical pore fluid pressure diffusion. It always combines something related to a volumetric capacity and something related to a transmission or conductivity component. One final observation. For an advective process, what we were talking in previous lectures about hydraulic conductivity, permittivity, steady-state seepage, we know the velocity of fluid flow from Darcy, which is K times I, that is velocity, and so the time scale is the size of our problem, let's say a certain length L, divided the velocity, which is Ki. It is the time it takes to travel, is distance divided by velocity. So L divided Ki for advective regimes. For diffusive regimes, we can get a characteristic time, and the characteristic time for a diffusion process is always proportional to length of our problem square divided the diffusion coefficient, which in this case is CV. And so, if you want to know whether a process will be drained or undrained, check the time it takes to apply the load with respect to this characteristic time. So if you apply the load in 1 hour, but the characteristic time for this sponge to squeeze the water out is 1 day, you are going to load pretty much under undrained conditions. But if your application of the load takes 1 month, and the excess pore pressure diffuses in 1 hour, then your loading will be drained. That means that the skeleton of the soil is continuously taking the load, not the pore fluid pressure. To summarize, the standard one-dimensional consolidation equation that we have seen coming from Terzaghi is similar to other diffusion equations throughout the physical world. It is for a one-dimensional system with very important assumptions. But particularly, I would like to stop with this equation here. When we stop at this equation, we have a very general form, because you may remember that now we have nice formulations for what is the evolution of void ratio with effective stress. We show the power models, the exponential models, the hyperbolic models. We have different models for that. You can go back to previous videos. And we also have very nice models. There are also power equations for the relationship between permeability and void ratio. We don't have to assume that these are constant parameters, and we can keep them as part of our equation, but in order to solve them, we will have to put them in our finite difference formulation, which is the purpose of our next video.